Welcome back to Teaching the Unteachables, where we dive into teaching and learning methodologies for professionals like you. This episode brought to you by Regal Rexnord Gentech Motors, the leading brand in electronically commutated motor technology. Learn more at regalrexnord.com. All right, well, hello once again. Thank you all for joining Did You Know? Last month, we had the opportunity to hang out with Chris Mohalley from Regal Rexnord. Chris, how are you doing today again?
Doing great. Happy holidays.
Absolutely. Getting real close. Boy, we're getting excited, getting busy, and ready for a break. And
ready for the break.
Oh, my goodness. Absolutely. So we spent a lot of time talking about ECM constant airflow, our true variable speed ECM motors, and they are quickly gaining popularity in the industry, but they're not the most popular ECM motor out there, at least what I see out in the field. So today we're going to be spending some time with the constant airflow's cousin, constant torque. Very similar, but boy, they have some different command controls. So Chris, thank you so much for joining us. And for those that missed last month's show, it is out there. We got the live version of it, plus we've got the finished edited version as well on our YouTube channel, Institute-HVAC Excellence. So make sure to go check that out if you missed that one. And let's go ahead and dive on into this thing, and let's talk a little bit about constant torque ECM motors.
Sounds good. We'll start right in with what you said there, constant torque ECM and their applications. So last time we talked about constant airflow motors, and they're more applicable to the premium level HVAC systems. Constant torque motors are more applicable to the mid-tier and lower tier systems. But as you're going to learn, there's some characteristics that cross over, which I think the audience might find kind of interesting. These are multi-tap motors. Majority of them are multi-tap motors. I have to remember to change my teaching habits because the motors have changed in the last 5 years or so.
Exactly.
So the majority of them are multi-tap motors, very similar to a PSC motor, where if you want the motor to operate more or less airflow, you simply move to a higher or a lower tap value. And they're also constant torque, as you already mentioned. And as we did last time, we will delve into what constant torque really means, and especially what it means to airflow. These motors do perform very similar to a PSC motor, but we'll show exactly how similar and what that means as far as making airflow selections and diagnosing airflow performance issues.
Yeah, absolutely.
So what does multi-tap mean? I'm pretty sure it's, what I've said already is fairly plain, but just to make sure.
Yeah, manual selections. That's really what we're talking about.
It really is. So, really the main difference between a constant torque ECM and a PSC motor is they both have speed taps. And it's funny because we call them speed taps, but even on a PSC motor, they were never speed taps. When on a PSC motor, when you want to make it multi-speed, you tap the winding in multiple places, and each tap gives you a different amount of torque. Each different amount of torque is going to give you a different amount of speed based on the load. Probably went a little too deep there, but so these
makes sense to me.
we call these speed taps, but really each tap has a programmed level of torque, and that level could be either a % of maximum torque or an actual ounce feet of torque. That, and again, if I go to a higher torque level, I'm going to get more airflow. A lower torque level, I'm going to get less airflow. But I'll default and go back to what the industry's comfortable with, and we'll just call them speed taps.
And they look very similar. I mean, when we're talking about PSC motors, we had typically wires that were our selection, but on some of our manufacturers, we actually had plugs or sockets on the motor that was the tap selection. So when we look at our ECM constant torques, now we're going to see a similar type of plug. And so a lot of people are familiar with that particular look. When we're getting to the actual socket, we're going to go, oh, wow. All right. That's starting to look a little bit familiar to us, right? Well, what do they mean? What are we doing with each one of these taps?
So the main difference here, again, being an ECM, is we provide line voltage to the motor continuously. You've got LGN, line ground neutral. The N is stamped on all of our plugs, whether it's a 115 volt, 230 volt, 277, or 460 volt. It's always stamped as N, so the N changes meaning. Whether you're in a 115 volt motor, it is actually neutral. A 230 volt motor, it's going to be L2, and so on. And then the C, of course, is common. So like the constant airflow motors we discussed last time around, this motor is powered continuously with line voltage, and it is the low voltage, in this case 24 volts AC, that actually energizes the speed taps, tells the motor not only when to turn on, but the tap that's energized tells the motor which torque level to operate at. So the only other thing that I do want to cover, make sure I cover at least once, I'm sure I'll say it again because I often repeat myself, is on the OEM motors, these speed taps are programmed. So the manufacturer of the appliance gets to program the torque value that goes into each one of those taps. And that's where, as we discuss later, these motors look very simple at the onset, but then they can get a little bit more complex when you understand that every OEM can program them differently. So so tap 1 may not always be low speed, and tap 5 may not always be high speed, just as an example.
Yeah. Now I've ran into that before where they were, opposing. Actually had some that came from a manufacturer one time as a warranty replacement motor, and I got some calls from the field. Hey, these are not running at the correct speed. And I'm like, what do you mean?
Right.
And they're like, low is high and high is low. And I'm like, oh, that could be an issue.
Yep, exactly. So, the best recommendation I can give technicians is to really treat these motors just like you did a PSC motor. Go to the door schematic or the unit manual, where you'll find either the color chart like we did for PSC motors,
right,
or in this case, the number chart that tells you what each number represents as far as high, medium, low speed, or other. Some manufacturers will actually label them as the heat tap or the cool tap or electric strip heat or something like that. And of course, we'll have to confer with those manuals for our airflow, because it's a constant torque motor. It does not maintain airflow like the constant airflow motor. And of course, we'll get into that in a little bit. So let's dive right into what makes the motor so different. So almost all constant torque motors built by us and our competitors use this same, and I like to use the word standard 9-terminal block.
Okay.
CLGN 1, 2, 3, 4, 5. It comes up to 9. You got a blank in the upper corner next to N. So I call it a standard 9-terminal block. And us and the competition build our motors with the same block. Almost all of them are using 24 volts AC to energize the speed taps. So what makes them different? If you look at the diagram that's on the screen, we see, and I'm using examples of how different manufacturers program the motors. This one programs the motor with tap 1 as low speed and tap 5 as high speed. Just like with a PSC motor, if I needed my IC heat is connected to tap 3. So if I wanted to increase my heating airflow, I would move the heat tap from 3 to 4, and I would get more airflow. Very simple. So now I'll give you another example, and if you didn't pay attention, I'll tell you what changed here. It's like a Where's Waldo. Tap 3 didn't change, but everything else did. Tap 5 is now low speed, and tap 1 is now high speed. And to your point, if a technician is not paying attention to the speed taps, they may move them in the wrong direction, which, obviously you can probably figure out if your amperage goes down and your airflow goes down. I probably went in the wrong direction. You can go the other way, but it's just as easy to reference the schematic and know what you're talking about when you're working on the unit.
Right.
This next one is going to give you even more reason to focus on that unit schematic. So, and this is actually fairly common in single stage package units that use constant torque motors.
Sure.
Because and especially if they're all electric. So an all electric single stage package unit might use one speed for AC and electric strip, heat pump, AC, heat pump, heat, and heat pump and electric strip. It may use one speed for everything, and if it does, it comes factory wired to that one speed. Now there's actually a high speed that I can choose here, but the key to this diagram is there are 3 taps on this motor that are not programmed. They have no functionality. So if I put 24 volts on tap 3, the motor's not going to run.
Okay, absolutely. That makes sense. So it depends on how it was programmed from the manufacturer. No program, no run.
Absolutely. So if I'm used to working on systems that look more like the previous one, or either one, I might think that going up to tap 3 is going to give me more airflow. The motor shuts off, and then I'm wondering, well, do I have a bad motor? Because I don't know enough about constant torque motors. So this is really probably more important for diagnostics, but also important for that technician that shows up on the job. They've got a frozen coil or a tripped limit, and they move to it inadvertently. Again, package systems common, split systems very uncommon to have unprogrammed taps, but they inadvertently move to a tap that has no program in it, motor shuts off. I mean, I myself, if I didn't know better, would think something wrong with the motor.
Bad motor. That would be the call that would come in.
Right. That tap's not working. So
that is a fantastic, if we get anything from this entire program, that is some super good information.
All right. So here's another example. And this is pretty common in air handlers from one manufacturer. I'm not going to say who the manufacturer is. You see a low, medium, and high. And, if a manufacturer programs all 5, whether they program tap 1 is low or tap 1 is high, tap 3 stays the same. It's medium. And you might start getting the mentality that, well, the middle of the motor is always going to be medium. Well, that's not the case. If you look at this particular air handler, where they did low, medium, and high in 1, 2, and 3, and then they put tap 4 as the dedicated electric strip tap, and then C manual for tap 5, which my joke in class is always, well, that tap's never going to get used because the manual's never going to be left.
Yeah, they actually have to open the manual to read this one and know what it is.
Well, not picking on the technician that's currently on the job, but not a lot of manuals stay on the job site. So,
exactly. We're talking to the technicians that don't read manuals. We're just encouraging them. Everybody else does, and we're so glad that you do.
So this is my cue to throw out the RTFM. Read the full manual.
Full manual, man.
Those are some examples of the most widely format that constant torque motors are used in.
Okay. Not very many.
The 5 taps are 24 volts AC activated. The 24 volts AC turns the motor on. The tap selection determines how much torque it puts out. The manufacturer that programmed the motor tells you if it's low, medium, high speed, and away you go. Very, very simple motor. Funny that you mentioned earlier, PSC motors having terminal blocks. In the past 5-10 years, there's another competitor of mine that puts out a constant torque motor that looks like a PSC motor.
Looks like a PSC replacement.
That's actually, and I'm sorry for pointing that way. I've got it on my computer screen here.
That's right.
That is actually a constant torque motor with just leads, no plug.
Sure.
It has the same line, ground, neutral, common
Still has to
wires,
be wired the same way as the ECM.
5 24-volt wires for its speed taps. So very, very similar and also very widely used by one manufacturer.
Yeah.
We put out a new motor recently called the Insight motor, where we changed the plugs. We went from the standard 9-terminal plug to 2 different plugs, and that was released primarily in 115-volt motors for the fossil fuel market. So I'll talk about that in a little bit. And then there's also two communicated modes for constant torque motors. One of those communicated modes is called PWM, and one is called 9-speed. And technicians that are paying attention to the manuals or the schematics are probably already seeing these because they've been out for quite a while. But I'm starting to I do tech support for us, so I'm starting to get more and more questions on these. So I'm recognizing that the awareness has grown on these motors. Manufacturers will take one of our motors, a technology that's new to the industry. They'll use it, and it'll take technicians a while to actually notice that something's changed
different
in the appliance. So some of these have been around for a while, and I'll talk about that when we get to them.
Sure.
But that's the evolution of constant torque in one screen.
In a nutshell. Yeah.
Again, 90+% of what's out there is that standard 9-terminal with the 24-volt speed taps. You've got some still using wires only, and then you've got a couple of new terminals and PWM and 9-speed. So let's dive right into, unless you had something to add.
One little question. So a good comment, good question came in from Ray about, so how do you get the correct programmed motor for your application? One, you go with the OEM motor, or you go with a replacement motor and you verify what your CFM ratings were on your OEM motor, and then you just look on your new motor. I could be wrong, but that's the experience that I've had with replacement motors. How would Gentech approach that one?
Yep. No, you said it perfectly. If you want the exact motor that came out, you would have to go back to the manufacturer of that appliance, order it from their authorized distributor, buy the model number of the appliance to get the program motor that came out of it. But we do make generic motors that have all 5 taps programmed.
Yeah.
And it's just like with replacing a OEM PSC motor with a generic PSC motor. We can replace an OEM constant torque motor with a generic constant torque motor that has
Makes
5
sense.
speeds.
Yeah.
And as you said, I'm going to adjust my speeds until I get the correct airflow. So since it came up now, and it'll come up later again.
Oh, okay.
So I often get asked, well, I like to go back with OEM motors because then I know all I have to do is plug it in and I'm done. I don't have to measure airflow because, I put the OEM motor back in, and my contest for that is, well, what if when the system was first installed, what if no one ever measured airflow and adjusted the speeds to set it up properly on day one? And then I get the and the gosh golly and the kick in the rocks. And then I take it a step further and say, now I'm really going to blow your mind. These are constant torque motors. What if the static pressure today is different than the static pressure that it was on day one, even if it was set up properly? If my static pressure is different today, then my airflow is different today, and I still have to measure airflow. So bottom line is, you're going to have to measure airflow whether you're putting the OEM motor back in or a universal motor back in. So really, putting a universal motor back in isn't any more time than putting the OEM motor back in, as long as you're following industry best practice.
Yeah, absolutely. Jason Abjute from our team says this all the time. He says compressors don't die, they're murdered. And it's kind of the same way with ECM motors.
I love that.
ECM motors don't typically die on their own. It takes a lot to kill one, but boy, they can easily be murdered if they're not set up properly and they have too much static pressure. And
I would agree with that wholeheartedly. Yes, sir. So we'll move on to the first variation, if you will, which is what we call the Insight motor. Again, we launched this in 2019 with the 2019 fan efficiency regulation change. 115 volt only, but it has 2 different plugs. But if you look at it really closely, it's the same motor as what you're used to. You got the 9-terminal plug here, and I'm marrying it up to the 3-terminal plug for line voltage and the 6-terminal plug for low voltage.
Different configuration, but it's all there.
Yep. And so you're probably only going to see this if you're a technician in a fossil fuel market, because today we only make it in 115 volt applications.
Yep.
And which means it's fairly new to the industry as well, because it's only about 3 years old. Well, almost 4 years old now.
Right.
Coming up on its birthday.
Getting close.
There you go. And this motor is, by the way, also capable of the 24 volt speed taps, and also the PWM that we're going to talk about in just a minute.
Okay.
So just a minute. How about next?
Right. How about now? And next.
It's pretty bad when I'm leading in myself.
That's perfect.
PWM, and if you're not familiar with the acronym, it stands for pulse width modulation, and all it is it's a DC duty cycle. If I speed up the duty cycle, I'm asking the motor to operate at a higher torque value. If I slow down the duty cycle, I'm asking the motor to operate at a slower duty cycle. So from a really fundamental standpoint, if I think about the old rheostats, I turn them up and the motor goes faster, or the light gets brighter. I turn them down and the motor goes slower, or the light gets dimmer. With PWM, the OEM board has full control over the motor. If they send a really low PWM signal, they'll get a really low output out of the motor. If they send the highest, 100% PWM signal, they're going to get maximum output of the motor. So they literally have infinite speed control of the motor in PWM. One thing that technicians can, because again, the manual is not often on the site, the schematic may not specifically spell out this is PWM. But one thing that technicians will notice when the constant torque motor is used in PWM is tap 1 and terminal 1 and terminal C are going to be typically wired back to the board through a plug. On all of our 24 volt motors, the motor terminals are going back to heat taps, cool taps, fan taps, and if they're all wired, park or unused taps. But in the case of PWM, what they're going to find is it's not going back to a heat, a cool, a fan. It's going back to a dedicated plug, because you're not meant to adjust that tap. You're meant to leave that alone.
I don't want to put 24 volts AC on that thing.
No, and it's not going to be 24 volts AC. The PWM signal is created with DC voltage. So you'll have to, again, go into the manufacturer's manual to find out what that DC voltage is that relates to the PWM signal. And that signal determines the motor torque, which determines the motor's output. So on a PWM controlled motor, you're going to adjust your airflow with the dip switches. So here we are. We talked about constant airflow last time around and how everything's going to be set up with either dip switches or jumper pins, or, today's communicating thermostats. I'm going to go in and I'm going to adjust the menu selection. Now here we are with constant torque motors, and they're right back to that form of, we use PWM communication and constant airflow as well. And now we've got constant torque motors using PWM and being controlled by the dip switches on the board.
And you're going to be at the National HVACR Education Conference this year, is that correct?
I will. I'll be teaching a class, and I will have a booth there to answer any questions you have.
And bring your books with you if you want to get the book signed by the author. I would love that. If you bring a book with you, we'll make sure that we have a book signing of authors while we're there.
There you go.
So hopefully see you all at the National HVACR Education Conference. And we hope that you all come back next week and hang out with us. And next month, we're going to be back again with Chris. We're going to be talking about ECM condenser fan motors. And the following month, we're going to actually dive into some more characteristics of ECMs with airflow, and maybe we'll tear some motors apart and dive a little deeper. So if you have some ECM questions, get them prepared. And Chris, thank you so much for hanging out with us once again. I enjoy diving into ECM motors and getting a better understanding of these newer technologies.
Probably more fun than it should be.
Hey, I love it when I get the calls. I had so much fun on your show, and
exactly.
You had fun talking about motors. Do you realize that?
I look forward to these shows.
I do too. All right. Well, I think we're going to call it a wrap. We really appreciate everyone hanging in as long as you have. I know it's a lot of information, and we really enjoy hanging out with you and being a part of this HVACR and building science community. And Chris Mohalley, we will see you in a few weeks on the next.
Sounds good. I know it dates the show, but happy holidays to you and your families, everyone.
Absolutely, everyone. Thank you so much. We'll see you later.
Bye.